This video is on Le Chatelier's principle. So this is a principle that deals with stresses at equilibrium. So if something happens to a reaction that is reversible, how does it get back to equilibrium? So in 1884, Henry Le Chatelier studied equilibrium, and he noticed this regularity. So if there's a closed system at equilibrium that is changed, the processes will occur in the system that tend to neutralize the original change, meaning they're going to try to get back to equilibrium, kind of cancel that change or that stress out. So we call that change of stress. So if you apply stress to an equilibrium, everything on the same side does the opposite. So right here in blue. And everything on the opposite side does the same. And I'll explain this more when we do some examples. And what you're going to look for is you'll see a shift. So a shift occurs to the side with more increases. Okay, and again, this will make more sense when we get to some examples. So what are these stresses first that can happen? So there's 4 that we can do. So the first is a change in concentration of one of the species. So this could mean that we either increase or decrease the concentration, or it could be we're just adding or removing more of that species, that particular reactant or product. We could have a change in volume or a change in pressure. Remember, these two are related, and these two are going to be dealing with gases. And so, right, if your volume increases, your pressure decreases, right? They have that inverse relationship. The third one would be a change in temperature, and this is the only one that affects K. Right, your equilibrium constant, and I'll show you how that works when we get to an example, or we could also add a catalyst. All right, so now let's do an example, and I can explain what this shifting means. Okay, let's say we change the concentration. So I've got this reaction here, and let's say I double the concentration of CO2. So here is my initial change. I'm going to take my CO2 and I'm going to double it. And all I'm going to do is I'm going to do arrows. Are they increasing or decreasing? So if my CO2 increases, what happens to every other reactant and product? So let me go back to this for a second. What we wrote and underlined in blue here. Everything on the same side does the opposite. So I've got NO on here, and it's on the same side as the CO2, that concentration increased. So the opposite would be it would decrease. Now everything on, if I go back here, the opposite side in green here does the same. So by that I mean everything on the opposite side of the reaction does the same as your initial one. So these are going to increase, just like my CO2 did. Okay, so same side, that's this NO, right, does the opposite. Opposite side does the same as my initial. So here was my initial, here was my start. Okay, so now I go back to here, and this thing I wrote in start, the shift occurs towards the side with more increases. How is it going to get back to equilibrium? Well, I'm going to look at this, and I'm going to say, I'm not going to look at my initial, but I'm going to look at everything else. I have 2 increases on my product side. What that tells me is that this will shift to the right. And another way to say that would be that it favors products. Meaning to get back to that equilibrium state where our concentrations and everything are constant, we're going to shift more and reactants are going to make more products to balance that back out. Okay. Now, the second part of this question is what happens to the K value? Well, we didn't change the temperature, so nothing. That only changes with temperature. Okay, so let's look at one that has a pressure change or a volume change. So let's say in this case, N2O4 as a gas makes 2 NO2 gas molecules. So pressure can be increased by decreasing our volume, right? We've got that inverse relationship. So if pressure is increased, the equilibrium shifts to favor the side with the least number of gas moles. So we're not looking at increasing or decreasing. We're just going to shift towards the side with the smaller number of moles. So in this reaction right here, what happens if pressure doubles? So pressure increases. Well, I have to look at how many moles I have. Right here, I have 1 mole because there's nothing as a coefficient. On this side, though, I have 2 moles. So it's going to shift to the side with the least number of moles. So it's going to shift to the left. Or another way to say that, oops, I'm going to write it like this, is that it's going to favor reactants to get back to equilibrium. All right, so what if I change the temperature? This is the only one that changes K, that equilibrium constant. You have to know which side of the reaction has the heat, so exothermic or endothermic. And then for the most part, when we increase temperature, it's because we're adding heat. So that's the assumption that we're going to make. So it says, what is the effect on increasing the temperature on the following exothermic reaction? All right, so exothermic means our heat is being released on the product side. So I'm actually going to write on the product side plus heat. Okay, so now I'm going to do what I did before with the increase decrease. So I'm going to increase the temperature. So heat over here is increasing. So remember, anything on the same side does the opposite. So my NH3 is decreasing, and anything on the opposite side does the same. So these are going to increase. So I have more increases right here on the reactant side. So it's going to shift to the left, or it's going to favor reactants. Now let's talk about what this does to K. Okay, so remember that K is your concentration of your products divided by the concentration of your reactants. And let's look at what's happening here. Our product concentration, that's the 2NH3, is decreasing. Our reactant concentrations, both of those are increasing. So you're going to get a smaller number in the numerator and a larger number in the denominator. When you get a larger number in the denominator, you divide by a bigger number, you're going to get a smaller value. So K will decrease. If you had an increase in your products more than your reactants, you get a bigger value on top and a smaller number in the denominator on the bottom, and K would increase. All right, the last stress is adding a catalyst, and you know by now that this lowers your activation energy. So it decreases the amount of time taken to reach equilibrium, but it does not affect the composition of the equilibrium mixture because this increases the rate in both directions at the same time. So this does not actually change. It's not a stress that it's going to change for us to get back to equilibrium. So that is Le Chatelier's principle, the stresses and how these reactions get back to equilibrium.